Yeah, thank you very much. It's my honor and great pleasure to announce our speaker today, Matthias Scheffler from the Fritz Haber Institute in Berlin. Matthias is a theoretical physicist from background and now isn't looking at the big world, but at the very small world, the world of electrons and nuclei. He actually obtained his PhD in Berlin, then moved to Braunschweig as a scientific staff member there, and then very early on in his career actually became director and actually founding director, also co-founding director, I believe, at the Fritz Haber Institute of the Max Planck Society. It is called Fritz Haber. It is that Fritz Haber that very closely worked with Carl Bosch on that process that is installed right when you came here in front of the museum on the Fritz Haber process. Haber-Bosch process, of course. And since then remained at the Fritz Haber Institute. He is also a distinguished visiting professor for computational material science at the University of California, Santa Barbara, where he is a very frequent visitor, so he is traveling back and forth regularly since 2004. He also holds actually 3 honorary professorships at all 3 universities in Berlin. And his focus is electronic structure theory and calculations. He has augmented in the last many years already at the forefront of machine learning for material science, I would say, these pillars of theoretical sciences for material science, computational simulations, has augmented this by machine learning and big data analytics. That's also will be a focus of his talk today. So his focus is really to get to novel, really unseen materials by these approaches with the help of electronic structure theory. Before I hand over, I want to mention some of the very many awards and honors you have received. Matthias, as you're a fellow of the American Physical Society, a member of the Leopoldina, the German Academy of Sciences. You have obtained an ERC advanced grant and you have an honorary doctorate and won also the Max Born Medal of the German Physical Society. With this, I stop here and I hand over, and I'm very much looking forward to your talk. Thanks for coming to HITS.
Yeah, so thank you very much, Frauke and Michael Strube, for having me here. And yeah, it's a great honor, it's a great pleasure. Also, in fact, having, as Frauke just said, actually being at a place which has the names which are very much related to the history of my institute. So Fritz Haber was the first director of a Max Planck Institute, which was called Emperor Wilhelm Society at that time. And the spirit is still there. And maybe I say some words later about Haber, about Bosch. And in fact, the other person who's frequently forgotten a little bit, but actually you also have an auditorium here, which is Alvin Mittasch, who has done a lot of this work which I think is a pre-runner of what I'm telling you, namely high throughput screening of materials. Okay, so this is actually what I wanted to talk about. What can you do when you do studies? And as Frauke said, I'm originally and mainly really an electronic structure theory person, but we see more and more that you should do more with the data. And one thing is artificial intelligence, which I think is in fact also defining a completely new idea, a new line of thinking how you should do research. And so I will do in the beginning a little bit in telling you what is different to the research we are doing now and in the future compared to the research we have done in the past. And this is called the new materials research paradigm. Before I do this, because I also learned that you don't have too many material scientists here. I mean, you're doing a lot of work. We just heard astrophysics, another new colleague, which is great. But on biophysics and linguistics and other things. But let me tell you very briefly why material science is so important. And what you see here is just really, this is very flat, but you will hopefully get an idea. So what is so interesting in material science, why is it important? And in very simple words, I would say materials are an essential foundation of our prosperity and lifestyle. Basically every new product, if it's a new and interesting product like your iPhone or actually a new artificial teeth or something, all this is built on new materials which we didn't know before. And to keeping this standard, in fact, requires to develop new materials. And this is in fact what we started with European Center of Excellence, which is called NOMAD. NOMAD stands for Novel Materials Discovery, and most of what I'm telling you has been really developed in this NOMAD Center of Excellence, starting and making developments and making predictions of new materials which could be useful for maybe something. On the other hand, I have to say we have very good contacts and very close collaboration with experimentalists and also with industry, for example, particular, in fact, with BASF here. There's not really, this is not really what drives us most, but actually it's really a pleasant thing. Now, why materials are important can be very nicely summarized by a speech and a program from the Americans. Every American president has to come up with a science initiative. And the science initiative of President Obama was called the Materials Genome Initiative. And now it comes further, for global competitiveness. Now, I tell you in a moment what this really means, but let me actually start with this competitiveness and some words by Obama. So this was launched in 2011 to help business. That was the main thing. Discover, develop, and deploy new materials twice as fast. We are launching what is called the Materials Genome Initiative. The invention of silicon circuits and lithium-ion batteries made computers and iPads possible. But it took years to get those technologies from the drawing board to the marketplace. We can do it faster. And so the idea is getting the information together and make developments faster. I say something about this in a moment. This is, in fact, the booklet which came to it, which is, in fact, quite interesting that the White House produced something which I think is really worth reading. Okay. I didn't want to say it this way, but so here's some other words actually from this booklet, Compute or Measure the Basic Properties Genes of Many 10,000 Materials and disseminate that information to the materials community to enable rapid searches and design. Now, the word genes, and they really admit this when you talk with them in private, was really just chosen to be a catchy word. There are no genes in material science. So what they mean is really having some specific properties of a material, but at the end tell you a little bit more how this material will behave. But of course, having a gripping title, they felt is important, and therefore this name, Materials Genome Initiative, just really an artificial thing to really make the public interested. Now, the nice thing is that I was working in this field anyhow already, so then it's actually good having such a program. So then the question is, what are we doing with this? Now, the first thing, it was said compute or measure, so my business is compute the basic properties. But there are two things where we felt what was considered there and what still is actually considered to be important in America is too short in thinking. Namely, 10,000 materials and enable rapid searches and design. Let me add here what had been done in 1908 and when Obama said we can do it faster. So basically what you also see when he says we can do it faster, he had shown several examples where you had the first example of a new material and then it took 20 years that you could do this material for something useful. Now here at BASF, or actually in Berlin, Fritz Haber showed by just a few drops that you can do ammonia from the nitrogen of the air and water. From this measurement, a few drops in 1908, it only took 5 years that BASF could produce several tons per day. So if actually there is communication that industry wants, that actually is certainly possible. Now, ammonia is the biggest invention which I think mankind has, in the sense that I think half of the population would not live without the Haber-Bosch synthesis, because it's really used for fertilizer. But of course, what also helped, unfortunately, to make this fast was the First World War, because it's also used for gunpowder. So there are always, when you do science, two sides of a thing, but nowadays I think but Mittasch in fact did. So Fritz Haber had the first demonstration with ruthenium that it worked. Mittasch used 20,000 examples to find the best catalyst. So he did actually, he was the first guy in these few years, in 2 or 3 years, 20,000 materials to screen and to see which one is the best one. And the one that Matthias has found is still nearly the same, is still used up to today. So that is some of the history where we are doing things, but of course we think we should now do it different. So the first thing, 10,000 materials, I think is not enough, because we are really looking for needles in a haystack. So if you really would actually just look around and look, is this material and this material and this material. In fact, the number of materials which are known to exist are 240,000. But in fact, then if you ask, they are known to exist, but do you know the properties? Do we know if they are electric conducting, if they are transparent? No, we don't. Actually, less than half we know that these properties. But then you also think, 240,000 materials, is that really all? And then you see, no, a lot of things are really surface related. These are inorganic materials, 240 inorganic. So there are also organic materials. There are organic, inorganic hybrids. There are nanomaterials. So altogether, in fact, the number of materials is it's practically infinite. So there's an enormous amount of things, but then you ask for very special things. If you look for the hardest material, the materials which has the best transparency, the material which has the best heat conductivity, there's only one. This is diamond. Now this one we know, right? But you can be sure there are other materials which have combined systems, and finding them, one out of practically infinite, is an enormous really question if you don't have a lot of experience. And of course Matthias had a lot of feeling what he should look for, and you need this experience. So 10,000 alone is just actually not good enough, because you may just look for the hay and not really in the region where the needles are. And then enable rapid searches in design. The idea is if you have all the materials in the book, you just look them up and you find what you're looking for. But if you have practical infinite, that also is not the good thing. You should not just really just have the data and look for it. You should do more. And this is what we think is artificial intelligence. And that brings me to the question how we want to do this, and why does this change the way we are doing science so far. The introduction of a new, or actually, this is actually more history now, because I thought I have a little bit more time, new paradigms to material science and engineering. So how did science develop over the last several thousand years? Science started, in fact, in the Stone Age, when people started in learning how to deal with fire. And in fact, it then started, I would say, in the Copper Age, which was just before the Bronze Age, where with fire, that was the foundation of metallurgy, how to really create metals and use that. That was experimental science. And in fact, this way of doing science, we are still doing this today. Now we are maybe not using fire from wood, but we may use a laser. We may use a free electron laser to look how electrons are moving in a molecule and so on. So experimental science is still there and still very, very important, and probably still the most important one. So when a new paradigm comes, this is in fact a philosophical wording that some people argue that a new paradigm means a new line, and everything which was there before is of no value. That is actually wrong. A new paradigm means a new line of thinking, but the other line of thinking is still valid. And so in the end of 1580 and the whole 1600, a new way actually started, and that was theoretical science. So the names there were Tycho Brahe, Kepler, Galileo, Newton, Leibniz, where in fact the last two, Newton and Leibniz, were the ones which not only started in designing equations which describe nature, but in fact they also introduced differential operators. So that was Newton and Leibniz. And so basically in the 1700s, or so say 1640, 50 something, the second paradigm is describe things by analytic equations. I'm using the one which we are solving, the Schrödinger equation. And again, this continues up to today. The laws of classical mechanics, electrodynamics and so on started around this age. Then something about 1950, 1960, again a new paradigm came in, and that came in with the availability of computers. Having equations like this one, or even the Newton equations for systems of many particles, is nice, but in fact these equations you cannot solve. So that is actually maybe not so nice then. But you can solve them approximately on big computers. And so in the 50s and 60s, methods like Monte Carlo by Metropolis or molecular dynamics or density function theory of electronic structure were developed. And that is then what is called computational science. This is the work which a lot of people here are doing, which we are doing, either in classical molecular dynamics or in quantum molecular dynamics using density function theory. So that started in 1950 roughly. And again, it's a new way. You solve an equation which you could not really solve exactly, but you solve it numerically. You do statistical mechanics. And then you have results, and you treat these results a little bit like an experimentalist would look at results. So that's why you also call this sometimes computer experiments. Something which wasn't there before, and it was possible with having computers. Now, since 2011, 2012, something new is coming, and this is what I'm talking about, is big data-driven science. The fact that we now have not just 3, 4, 5 data for a certain thing, but we may have actually several hundred, several thousand, or even 1 million of data points, gives you a completely different way to look at it, and I want to show you this in my talk. That means you are not looking for an equation anymore, but we are looking, is there a system, is there a pattern, is there a structure in the data? So somehow we look at data by themselves, not really with the prejudice that we want to have these data for something particular using them, but we look, is there structure in the data? And having the structure, we then actually continue and get an idea, what does the structure tell us about the system? That in fact also means that we are giving up a little bit of the old thing. We accept that some properties cannot be described by an equation. Very often things may be very intricate. That means some electronic structure, chemical bond, plays a role which then in statistical mechanics has this and this possibilities. And at the end, if you look at catalysis, where a lot of processes really play together, that means at the end, you cannot really describe this by a simple equation. But if you have a lot of systems, you may find patterns and structure. And so giving up the idea that you want a scientific equation, but going to structure, but then we come to a little bit changing of what I just said later, is what is the new paradigm. That started with a talk by Jim Gray at a Microsoft workshop on January 11, 2010, the 4th paradigm of data-intensive discovery, where he described that. That was basically his last big thing, because 2 weeks later he went missing on the Pacific. And later then his colleagues have published the workshop program. But therefore, this idea that with big data you can find structure which you would never see if you only look at a few data points. And that's why you get actually new ideas and new insight. And I show you where we are, what it can, and actually also what it does not, what it is not able to do. So there are words with this, and I have to say that there is not really a complete consensus, and I mean, what is this and what is the other one? For me, these 3 words which you see here are essentially telling you the same thing. So in all things, it's learning from data. Of course, learning from data is what we always did in science. I mean, without data, you cannot really do science. But learning from big data, looking for structure, there are many, many methods and concepts, and it is very interdisciplinary, which you will also see during my talk. I think the umbrella term is now mostly artificial intelligence, learning from data and guessing something out of it. But you can also say machine learning. Whenever you learn from data, that is machine learning. We have used typically, I would say, big data analytics. That all should mean roughly the same, at least in my nomenclature. Some people think there are slightly differences, but actually there's no agreement on this. Of course, there are many more terms which are used in this field. It could be bioinformatics, intelligent systems, cheminformatics, robotics, subgroup discovery, data mining, computer science, data compression or compressed sensing. I think signal processing is what is behind that as well. So there are many, many, and even more. And if you look at machine learning, the classical programs or methods which we are using in machine learning, and which we are also using in some examples of my talk, is neural networks, support vector machines, and kernel-rich regression, and so on. So a lot of different methods coming from the different fields. compressing a signal. At the end, what you see is a thing which we're actually using, but for a completely different purpose. So it's very interdisciplinary and very interesting in developing new methodology. So what is the problem? So we're talking about big data, and what are we facing? Now we are also having Max Planck network on big data driven material science, and they're all fighting first of all with the same thing, a thing which we didn't have the problem in the past, and that is typically called in computer science the 4V, where the V stands for volume, the amount of data, variety, the heterogeneity and of the form and of the meaning of data. When different people measure or give you some data, actually there may be a very different meaning, and so you need to know this before you can actually put things together. Velocity at which data may change or new data arrive, and veracity, that's what they mean with this, the uncertainty of the data quality. I mean, if you have data where, let's say, say more than 20% are wrong, that is a problem. If actually just few are wrong, maybe that's not a problem, although you have to be careful, because when I said you're looking for the needle in a haystack, if just the needle is described wrong, and then you may also not find it. So one has to be very careful also with veracity and these things. In my field, material science, it turned out that we don't have really a problem with volume. We expected some, but then we found a lot of ways for efficient compression. We have a big problem with variety, and I tell you a lot about this in a moment. We don't have a problem of velocity because, again, the things which I'm calculating, usually you do a calculation, and this calculation takes 1 million CPU hours. So the data then come after 1 million CPU hours. Of course, you do this in parallel, so it doesn't take 1 million years, but or hours, but still actually they don't really come that fast. But veracity is the problem, in particular if you look at data coming from different groups. You have to really look on different methodologies. So there we are actually doing a lot of work in this. But what I think you have to deal with the 4V, and that is actually interesting, but the science is in the analytics. You want to do science with the data, and this is big data analytics, and I said that before. There is structure in the data, there are patterns, there are correlations. Things which you don't really think maybe correlated, and these correlations tell you about materials which you have not seen so far. But you found a correlation, you can look then outside the data we have seen. And the way I've plotted it is that you maybe at some point, if you have a good descriptor, a description, which we don't know what it is, these are the genes basically, the essential properties which we don't know, maybe you can make a plot, most likely not two-dimensional, but maybe some type of plot, where you say, if I have a descriptor here and a descriptor there, and this material in this area, that will be transparent metals, which I need for a touch screen or for something else. Or there are sensors, or there are photovoltaics, so that I can look and make a map of materials helping me to find materials which I have not seen before. That is a dream which we have, looking really just at structure. That was the motivation of this NOMAD laboratory, this European Center of Excellence, but in fact has 5 components. The first thing is, of course, you have to collect data, a repository or the raw data. It's very interesting that when we started 4 years ago, actually we started even earlier, but when we started, there was no sharing of data. Basically, people just kept their data on their own computers. There was no culture of giving things away. And the argument was, in fact, even, I mean, I did so much calculation, so much work with my data. This could be a gold mine. Why should it give it to someone else? But of course, if you don't really work on the gold mine anymore, why not? And I think it's really dishonest, right? It's not scientific. I mean, if you have data, you should not only show the few data points which you publish, but there's much more information in the data which you don't publish in other people. You will be really surprised what people can do with the data, and I show you this also a little bit. But then there is the archive, I tell you, which is then, this is actually raw data, but of course to do science you need normalized data. We then have what is called an encyclopedia. So looking at the data is very, very important. You want to plot them, you want to identify them, so you need something which shows you that. I will show today or concentrate only on big data analytics, but of course also dealing with data, in particular for outreach, I have to say, but also somewhat to understand data better, is visualization. So there's some virtual reality. A lot of things are more than three-dimensional. So an electron in a solid, you want to be an electron, and you want to see where where the other part, and so you want to really look around and find that. And so there's a lot of visualization tools as well, which we don't have the time today. So I will mainly actually talk about the analytics. So the first thing, the entry, is getting data. And so we started many years ago, actually 5 years ago, with what is called the repository, convincing the other scientists in my field that you should share data, that by sharing data, everyone will learn and help science much more than keeping the data themselves. And the request that you should keep data open does not mean that you only keep the data which are published, this graph open, but it, I think, means that you should actually keep all the calculated data open. And this is what we were pretty able to do. And in fact, with all the conflict which we had, that we had to convince the community, we now have many more data than we ever had expected. So we now have the repository with 50 million total energy calculation. And that is actually several billion of CPU hours on the best computers in the world. So a lot of computing time which was spent. And in fact, there's something where our philosophy is completely orthogonal to the standard way, where in the standard way you basically publish your results, already viewed in what you consider results for a certain question. We say no. We want to evaluate the accuracy. We want to really look at everything. We want to also use the data for something else. Even if I've done something for, say, titanium dioxide, which is the white in paint or toothpaste, pigmentation. But titanium dioxide is a very important material in catalysis. It's a very important material for photovoltaics in organic, inorganic cells. So if I have all the data, I can reuse the data for something else. And so we, from the very beginning, said, if you want to join this thing, we need all the input and all the output files, and we need actually the codes to get everything there that other people can evaluate really what was done. And then, in fact, even a calculation which was done under some approximation, but in the range of many calculations, they make a lot of sense, because you can look into trends and structures. How do things really change with a certain approximation? Now, we have 50 millions because we also, because we are not really looking at our codes. Of course, we have all our, we have a code at the Fritz Haber Institute, other people have other codes. So in my field, there are somehow like 30 to 40 different computer codes. And we felt we should support all of them, not just the one which we like. So we support all of them, and here you see somewhat the number of total energy calculation for, I think, the biggest one, the most frequently used, which I think Frauke is using Orca. Of course, we are using FHI Ames, but then there are many other codes. The biggest one is VASP. And the reason why biggest one is VASP is that the American, where this genome project was started, the Americans, they are using VASP. And so the biggest databases in computational material science in America is AFlow at Duke University by Stefano Cottarolo. It's OQMD by Chris Wolferton in Chicago, and Gerd Seder and Christine Persson have the materials project in Berkeley now. It started at MIT. And in fact, if you want, if you look really at, for example, OQMD or the materials project, you can find certain properties. You can find the band structure of the electrons. You can find this and this property, but you will not get the input and output file. So if you want the input and output file, you have to go to Nomad. So basically, they all gave actually their codes, their results to Nomad, and that's, in fact, by 90% of all the VASP calculation are really coming from these colleagues in the USA. So what we offer is, we request that everybody uploads everything, but then we guarantee that the code, that the data are kept for at least 10 years, and at least refers to after the last upload. So as long as people are uploading, we will actually keep the data there. Data are open access, but in fact we accept that some people feel they are still working on the data. but it may be useful that they have them on the archive because they want to share them with some other collaborators. And so we say actually you can actually define a delay time of up to 3 years. Very few are doing it. So when I said 50 million, these are the open access data. So there are more data, but the open access are 50 million. So we are not looking at the other data at all. And of course we provide digital object identifiers which makes data citable so that in a publication you just give this thing. Now I already mentioned that there are 40 important codes in the community, which is, I call it material science, but these are people from physics, from chemistry, from really materials engineering, and they all speak a different language, in the sense that the same term, be it energy, actually has a different meaning in the different fields. The units are different, right? I mean, be it electron volt, be it kilocalories per mole, or be it whatever. So the data which you get from the different computer codes, if you just look at them, you can't really do very much. If you are not really an expert of the computer code, you cannot do very much. Of course, for an expert, it's very good to have the repository. Also to fight against scientific misconduct, it's very good to have it. But to use these data from different computer codes is nearly impossible. Now, of course, then there was the idea 5 years ago that why don't we define a common standard? I mean, everyone has a standard, and I felt, yes, actually, if people want to follow one standard, they should. But I guess it's probably like electricity. If I travel to Australia or England, I need a different plug. I need a converter. I mean, I can wait that everyone is using the same plugs, would make a lot of sense, but I think it's much more realistic to think you need a converter. And if you deal with people, it's better to having a converter. And that's what we did. We did a lot of work to build converters to what we think is a good standard, but we don't really request that other people are using this. Everyone uses what they want to use, and we have developed the conversion layer. It sounds very simple. But let me just tell you, this was 20 people working for 2 years. So actually understanding the code and really getting this information out, what is really meant by this quantity, is much bigger work than necessary. But now it's done. So now we have these converters for actually 40 different codes, and we have this archive so that we can now work on the archive with the different methodologies. Now, there is something which I think still is a shame. We have solved it a little bit, but in fact, in general, I would say in most of the sciences, it is not really solved. And I'm just quoting here from a Nature editorial, what I just described to you, which we have solved, they described a year ago and called it empty rhetoric over data sharing slows science. Means that everybody talks about that sharing is good, but nobody does it. Government, funders, and scientific communities must move beyond lip services, talking, and commit to data sharing practices and platforms. I can tell you that we are doing this. We are now, in fact, developing this to an eingetragener Verein with a lot of funding people and institutes. But I can also tell you it's very, very difficult. The German research organization says actually we are due for funding research, not for infrastructure. Everybody says actually this is not our field. Everybody says yes, it should be done, but nobody actually wants to give money. No, we somewhat succeeded in getting it, but it was an interesting experience to talk with these people. Why they think it's necessary, but the others should pay. We are really on the road and doing this, and I think we will probably discuss that. And as I said, in computational material science, we have solved that. Okay, so this is where we were with the veracity. Actually, variety, I told you that we have so many different codes and we have these converters. Veracity, I don't really have the time to talk about it. But also there, having so much data, we developed some analytics tools which tell us what is this data, this calculation good for. I mean, a lot of calculations, I would say none of the calculations we have are bad. But some are good for this purpose and maybe not for this purpose. And so we are doing this in a friendly way that we say actually some calculations have some approximation, that's why they're only good there. But on the other hand, if you have a lot of calculation for the same system, I think for silicon we have 500 calculations for silicon with different approximations. If you have that, you also can actually get an idea even from a calculation which is not so good, you can make an extrapolation to what the good value would be. So that is also solved by this NORMA thing. Now let me give the old, I told you about high throughput screening by Alvin Mittasch, but here is somewhat what motivated me 5 years ago in why data-driven science gives you new insight, even if you don't understand it. The periodic table by Mendeleev. What Mendeleev did, he measured the weight and the chemical activity of atoms. And doing this, he put them in some order. Now, when Mendeleev lived, only 50 or 57, I think, atoms were known. Now we have more than 100. So a lot of these spots were actually empty or white spots. For example, there was no gallium, but he put them in some order. He had no idea why this is a structure. Why this is a structure only became clear after we knew quantum mechanics. If we knew that there is a cell structure of electrons, the S shell has 2 electrons, the P shell has 6 electrons. Only then we understood why this system has this type of shape. When Mendeleev did it, it was just data and finding a structure in data. And this is what we want to do. But of course, we want to do it for materials. Right? So in principle, you can say, actually, before I say that, let me actually say, I mentioned gallium. So gallium was not known, but there was actually known that there should be an atom. Right? I mean, there was something missing there, and it was even known how this atom should behave, because it should belong to this column. So in fact, this is why, what do we think? Find structure and then get an idea what is missing and for what this missing thing could be good. But of course, we want to do this now for materials. Organize materials according to their properties and functions. Now, there are 100 atoms, so that was complicated by the time. There are practically infinite number of materials, and you may understand why we are still working on this and haven't solved it yet. But it's really much more complicated, but of course it's challenging and interesting. So here are the systems we have looked at, and I will choose 2 or 3 of them in the next couple of minutes. So one thing, a general question, can we predict what structure a solid will have? A structure means how many neighbors will each atom have? So a classical system would be the so-called rock salt structure or the zinc blender. So rock salt is the one what you put on your egg, and the zinc blender is what diamond or silicon has. So one has 4 nearest neighbors and the other one has 6 nearest neighbors. If I give you 2 atoms, could you tell me these 2 atoms will form as a stable system rock salt, or will they form zinc blender? So this is one thing which we have looked at. Another thing which I'm not sure if I have time is a new oxide. Oxide which could replace standard semiconductors, indium, aluminum, gallium, where they all have a certain ratio, X, Y, Z, where the sum should be 2, and O3. One of these systems, you know, maybe aluminum 2O3 is a known thing. But in mixing this thing, there is the possibility that what now is becoming light-emitting diode for our lightning by gallium nitride, that you could actually do something with even higher power and more stability, and maybe actually also a new type of transistors. And playing around with these things, we hope that we find something new, and people are starting to be able to grow these things. So 3 years ago, actually, no one could actually create these things, but there are institutes now in Santa Barbara and in Berlin who are able to grow these type of structures, and we just start in predicting what structures could be particularly important. When I've said before, maybe there are only 2 structures, like actually maybe for octet binaries. For these things, there are at least 5 different structures which have different symmetry and with different number of atoms altogether. Perovskites are a most promising group of systems. I don't have the time. There's something which is called the Goldschmidt tolerance factor, an empirical finding. We have found by machine learning a somewhat better working thing. I will talk about topological insulators. Finding such a map, and I tell you about the descriptors X and Y later, where we can say if you use a material which belongs in this point from the X and Y coordinates, it will be a topological insulator. It will be here, in fact, it will be also maybe a topological insulator, it will be a metal, or it will be a trivial insulator. And I probably take this out, which is the carbon dioxide thing. We'll see actually how we do with time. So let me actually first explain to you the problem. And I do this for our first example, the octet semiconductors, predicting if a system is rock salt or zinc blender. Now, of course, you can calculate this. So these are the two structures. As I said, here every atom has 4 nearest neighbors, and here every atom has 6 nearest neighbors. Very different symmetry, very different behavior. You can usually put these atoms in both of these structures, but then they behave very, very different, and only one will be stable and the other will be metastable. You can calculate that, of course, but then, of course, you need a lot of CPU time. You can calculate that, and just ZA and ZB are the nuclear quantum numbers in the periodic table, and the color code tells you red means it is zinc blender, dark red means actually it's very stable, a little bit more open, like here, it means it's actually not so stable. Dark blue means it is very stable in rock salt, and depending on the color code, it's actually the energy difference. This is not a map, right? I mean, this is results which we find. Can we rearrange that to find a map? Can we do a coordinate transformation, I would call this? So that at the end, we have coordinates, which I call descriptors, or D1 and D2. You can also say genes. That we say there is a borderline. Everything left of the borderline is rock site. Everything right of the borderline is zinc blender. Then we have the map idea, like countries, right? I mean, here is France and there is Germany. And basically the idea is, if I look for someone who's speaking French, I better go to France, then have a good chance. And maybe the D1 and D2 should tell us, so I'm looking for something which is rock salt, then in fact, you need a certain D1 and D2. If I look for something which is zinc blende, I look for them. This is the idea behind this, and I show you how we are doing this. It's a very old, that's why we choose that, a very old question in material science. But, so people have done these maps. And the key people who have done this are Jim van Vechten and J.C. Phillips, but they have done it with data which are very close to the result. So basically, their D1 and D2 was, for example, the interatomic distance, or this was the dielectric constant. Now, if you measure the interatomic distance, or if you calculate that, or if you calculate the dielectric constant, that's even much more complicated than calculating the total energy difference. D1 and D2 must be, in the terms of genes, very simple. They must be accessible without really knowledge about the whole system. And that is what is different to the history, but the idea in plotting maps is, of course, not new. And of course, how to find these? And there's no reason it's two-dimensional, so in principle, we should have an open description that it could be also higher dimensional. Most of my field, probably 90%, is doing kernel-rich regression in the machine learning business. I very briefly tell you about this, and then I tell you why and that we are doing something different. Statistical learning or machine learning by kernel-rich regression means the following. You have data, P. So that could be the energy, the stability. Or it could be also, say, the band gap of a semiconductor telling you if the semiconductor is red or blue, if it emits light. So you have data. And you have some coordinates, which are, at the end, our descriptors. A set of descriptive parameters. And you want that these data are written down as a continuous function. And in machine learning, you say this continuous function is some, in the beginning, unknown coefficients and a kernel, which depends on D1 and dk. And you go over all measured points or all calculated points. That means you have, say, 1,000 points, and you now write this down as a function which sums over 1,000 functions, which you define first, with coefficients which you really use. So this kernel, di, dk, could be in linear regression just a product. Polynomial, it would be a polynomial. What is usually mostly used is a Gaussian kernel. That means this kernel of di and dk is just an exponential with di dk divided by some width of the Gaussian. So it is a little bit like fitting a function with Gaussians. But when I was a student, actually 5 Gaussians was a lot to fit. Now you fit 1,000 data points with 1,000 different Gaussians. And 1,000 different coefficients. So in principle, that must work, right? I mean, in fact, it's even overdetermined, which we'll say in a moment. So this is what machine learning is. You fit this thing with a lot of Gaussians, with a little bit more thinking, which I show you in a second. And you then think this thing will also work as interpolation and maybe even for extrapolation. Oops, let me actually say, oops. So what I want to say is also, clearly, more data means a better representation. But what this always asks, the machine learns. Now you have to think a little bit more what learning really means. Learning has nothing to do with understanding. Do we learn anything? Because at the end of the day, you want to learn. And will we ever have enough data? And in principle, the more data you have, the better. But if things are so intricate, maybe you never have enough data. And there's a lot of impression that this may be true. So this is what we do now, statistical learning, which I showed you before, versus what we are doing, compressed sensing. Compressed sensing is a method coming from signal processing. You have a complex signal and you want to really reduce it to the essence, but you want to reduce it in a way that you can do very cleanly go back without a significant approximation to the original one. And the way we are doing this for material science is the idea of the compressed sensing, which you see in a moment. So kernel-rich regression, if you have just seen the function which we want to build, which should agree with our measured data points or calculated data points, is just a sum over Gaussians, but a lot. And we request that the difference squared should be actually minimized. In compressed sensing, you say we don't, so here I would say you assume that you know the descriptor. And the descriptor could be the atomic positions or could be something which you do with the atomic position. On the other side, in compressed sensing, you say, I don't know the descriptor. And because I don't know it, I use whatever makes some sense. And so I write down my analytic or my function as a scalar product, d times c, where d is a vector where every line is a different descriptor. So in principle, you can say this is a sum. This is d1 c1 plus d2 c2 plus d3 c3 and so on. And d are all possible descriptors which make sense. And what I'm showing you in a moment is the number of descriptors we are using here is something like 100 billion different ideas. So we start with 100 billion different ideas because we say we don't really know, and then we find the best ones. In the same way as on the left side, we minimize the error with respect to the known data points. Now I mentioned before, to do all this optimization, you need a so-called regularization term, otherwise you do some overfitting. In kernel-rich regression, you add to this thing a condition which is somewhat the so-called norm 2, which we all know. The norm 2 is a distance between 2 points. In compressed sensing, you add actually the norm 0. So the norm 0 is not a clean norm, but in fact it's very easy to explain. The norm 0 of a vector is a number of known 0 elements. So if I have a vector 5, 0, 0, 0, the norm 0 would be 1 because only one element is non-zero. 5, 2, 0, 0, the norm 0 would be 2. So we do the minimization under the condition that also the norm 0 should be small, which in fact means we try to find the description that most of these coefficients in this long sum are 0. This is the requirement. This is very difficult to fulfill because it's a combinatorial problem to, I mean, when I have actually just 4 elements, it's very easy to say what the norm 0 is, but the bigger the vector is, the more complicated it is on a computer. But this is the way. So we start with a lot of descriptors, and then we try to find the best one by asking that most of the coefficients should be 0. And as I said, actually, we can do this with 100 billion or even more elements. And the method we call sure independence screening and sparsifying operator. You will see a little bit why we are calling it this way and what is behind it. So we start, actually I'm being very fast, I will not really go through this list which you see in a moment. We start with some primary features which are properties of the atom. You could say that should be the nuclear numbers, but we think you need also things which are closer to the quantity you are interested in. So maybe the size of the atom, the electronic structure, the S state, or how much energy you need actually to take an electron out of the system, electron affinity, the HOMO level, and the radial, the quantum mechanical electronic wave functions. We all do this and include this as primary features. We do something of the dimers. I said in the beginning, we want features which are cheap to calculate. But it's also clear that these things will not enter directly. I mean, they will enter maybe in some power or some other formulas. So we are starting from the so-called primary features, and to build our CISO scheme, these are the two guys who in fact have done most of this, we systematically construct a huge feature space of 10 to the 11 elements. So we start with 23 primary, and then we add them, we subtract them, we multiply them, and so on and so on. A lot of mathematical operations. And doing this and combining this and doing this in a tree-type structure, you very fast go to 100 billion. I mean, it's very, to get this. But then you have actually a lot of formulas. And now the question, which of these formulas is the best one? And this is what sure independent screening does. This is a method which is described here by Fenn and Liv. It also means actually correlation learning. What is done is we calculate first a matrix of the feature space. So in this case, we had not so many elements. We just had 82 different elements, but we had many properties of these elements, many features. And so we built a matrix which is 82 times 100 billion elements big. And we had target properties, Y, from namely the energy difference for these atoms. So we make this product, and we then select the, say, 1,000 biggest elements from this. And with these 1,000, because we cannot really deal with 100 billion so easily, but doing this product is easy, and then using the 1,000 biggest one is what we are doing this. And then with the 1,001, we can do L0 minimization. We cannot do anything for getting close for billions, but for 1,001 we can do, actually for 10,000 we even can do this, and do really a clean L0 classification. Let me actually just skip this slide. This shows, in fact, how it's really done on practice. In the first one-dimensional descriptor, a two-dimensional, a three-dimensional, you first learn the best one, and then you learn the different vectors to get your description better and better. And then you get what you see here, descriptors, which look very, very strange. There is the S wave function of atom B divided by the P wave function of atom A, the P wave function of atom B divided by this squared, and so on, and something else. I don't think, in fact, that these formulas make much sense. I think the elements which enter the formula make sense, but the formulas themselves do not make much sense. But these formulas give us this map which we wanted. The green one is the border. Everything right of the green one is red. Everything left of the green one is blue. And in fact, what is very interesting, there are some exotic things. I mentioned diamond before. And we did, in fact, the learning without any information of boron, nitrogen, and carbon. And we were able to predict carbon being the most stable element which we have. Now, unfortunately, diamond was known before. Otherwise, this would be a fantastic paper. But it just shows you can do the learning and even predict from this thing what is going on. I have another 5-6 minutes, or should I basically skip this on the timing, which was an honest thing? Mm-hmm. So let me just very give you a brief thing about something also very modern, topological insulators or quantum spin Hall insulators. This is a system, this is actually a standard in a semiconductor. So you have a valence band, this is where all the, in K-space, which is not so important. Here are the electrons, and there's the band gap, and then there is nothing. And of course you can excite an electron from here to here, and this can then make a transistor, or you can make optoelectronics and so on. But you can, in fact, with some ideas, also invert this band structure in some way, and spin orbit coupling, alloying, strain is one option. And doing this means that at the end you have a band structure. Actually, maybe I should say, so I made it blue and red, and in simple words you can say I'm talking about gallium arsenide. And then I would say the blue means these states come originally from the arsenic atom. and the red one come originally from the gallium atom. But you can, in fact, by some ways in geometry and alloying, build something where this is mixed, so that somewhat this is maybe an arsenic state, but then already it starts getting gallium-like here, and just you get this inversion. The interesting thing is that these systems have very interesting properties. They have at a surface properties that they can conduct electricity without resistance. That means you don't lose energy when you have conductance, and this is shown here very briefly because there must be a continuous connection. If you have this band structure, the blue one must be connected with the red, and the blue one here must be. But these two states have different spins. In one channel, the spin is up, in the other, the spin is down. And that means that this electron will spin up if this electron moves along an edge, and it comes to a perturbation. Usually this is scattered and you have a loss. This cannot be scattered because if it comes to a perturbation, the only way to really remove in the other direction means you have also to change the spin. And so these things cannot really scatter, they just travel without seeing the perturbation. And that's why you have no backscattering and no resistance. So very promising materials. And so we looked into this. This was done by a Brazilian PhD student. And we looked at it for different materials which are just built from group 4, others which are built by 3 and 5 materials combination, by 2 and 6. And we added, to make them more flexibility, some other, these gray rows on the top, on the bottom. So these are hexagonal flakes, if you want, like graphite, or graphene, I should say, like graphene. But then they are functionalized by additional atoms. And we went through all this. And again, we do the machine learning, and we found this map. These are the points which we calculated, or which we tested at the end. But then we again found an X and Y axis, where the nuclear quantum numbers are there. They are the highest atomic level, the electron affinity, that means the energy you gain when an atom is added. And you see there is a range where we say here, it doesn't matter what functionalization, what of these gray atoms you add. These are topological insulators. Wherever you're here, where you are, you will find a topological insulator. If you're here, you may find one, but they are functional dependent. So some in these things depends. You have your flake, but on top and bottom you have something else. You find a region where you have metals and where you have non-metals. So we are able to create a map in telling where should be more topological insulators. So far only 7 topological insulators are known. So we predicted 70 more. Which should be easy to really, which should be able to create. The identified descriptors are cheap. They only depend on the free atom. That is not always the case, but here it was. And of course, we find a range which was not expected. Typically, you would have thought if there is a big spin-orbit coupling, you would find a topological insulator. But we found, in fact, a very interesting range where you can create things beyond really the standard picture. Okay, let me come to, actually, I'm jumping over this, which is more really Fritz Haber or whatever related, but you can use carbon dioxide for something useful, but let me, but we don't have the time for that. And because I wanted really to show one movie at the very end and finishing. Okay, I'm also jumping over this. Okay, this is what I wanted to show. So this is my conclusion slide, but after the conclusion slide are 2 more slides. So basically this is the amount of different materials is really huge. The materials which we have exhibit, if you look at certain functions, there are very, very few materials. But at the end, if you look at certain functions, the compound space is very sparsely populated. So we have a huge number of possibilities, but in fact we only want very few ones which are good for this or good for that. For having these functions in, and that's why CISO is so good, because it really takes this sparsivity into account. Now looking at big data and the way it's discussed, it's really a learning curve. So the relevance of a new technology like big data analytics always grows with time. And you think, and this is actually how it should go, but then you also see how it's actually reflected in the mind of people or in the mind of publication, again with all new technologies, in particular I would say with material science, the perception of the importance is very different. Right? I mean, I think we are here, but everybody thinks it's very important. I think we are not yet there. It's still a long way to go. So joining a field is good when you are here. I mean, if you would be at this level, then actually everybody is there already. I think we are here. There's so much more to do, and it's many more limits. It's an exciting field, but we have to be also honest. It's really oversold and a very big hype at the moment, but it's really very interesting. Okay, I'm also jumping over this. We had a very nice Kegel that would have been actually a little bit on doing the parallel to linguistic, but I don't have the time. So this is our web page, and I only wanted to show and finish with one YouTube movie, which in fact, because we have a mirror of this whole thing also in China, and YouTube is banned in China, so then you could look at UQ. And here we are, and just wanted to show you this at the end, which summarizes to some extent what I've told you.
The Nomad European Centre of Excellence, your gateway to material science data. This is John, an engineer in the sustainable energy field, who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation of electric cars. So what do John and Laura have in common? Well, to achieve their objectives, they both need to use new high-performance materials. So what can material science do for them? The ideal solution would be to provide them with a map of materials where they can identify and select what they need. Indeed, the amount of different possible materials is practically infinite. So what if all materials could be grouped according to their properties and functions? Is this already possible? Well, this is the idea behind NOMAD, the Novel Materials Discovery Laboratory. NOMAD is the European Centre of Excellence for Material Science Data, set up in 2015 to enable the quest for new and novel materials and their properties, and to reveal unknown properties of already known materials. The foundation of this European Centre of Excellence is the database called the NOMAD repository, which is available to all and based on open access principles. It hosts input and output files of all significant computational material science codes for at least 10 years, for free. It also enables a confirmatory analysis of materials data, their reuse and repurposing. As the NOMAD repository includes extremely heterogeneous data, which do not allow for direct comparison, these are being processed into code-independent, machine-readable and standardized form. This is the NOMAD archive, which provides the open access data from the repository in an easy-to-use and easy-to-access way. The archive is the base for the NOMAD Encyclopedia, which displays the properties of computed materials based on millions of calculations that have been performed worldwide. Not only does the encyclopedia provide information about known compounds and their known properties, but it also makes it possible to propose a previously unknown material with the desired characteristics for a special application, or to bring to light the previously unknown properties of known materials. The NOMAD COE also provides a set of big data analytics tools that uncover structure and correlations in big data of materials. This enables scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus of future studies. As seeing helps understanding, NOMAD is also developing a virtual reality environment to allow for interactive data exploration, training and dissemination. Clearly, all of this is made possible by the underlying NOMAD high-performance computing platform, which consists of a distributed multi-layered storage system connected to scalable computing capacity. Data is the raw material of the 21st century. If you deal with material science, the NOMAD Centre of Excellence is your gateway. Start using it now at nomad-coe.eu.
Okay, thank you very much.